I come from the US, the Environment Modeling Center under National Center for Environment Prediction. I will talk about dynamical code for our current developing and the future frame. And most part of the I present somewhere, so if you listen before, bear with me. And how to change in the next one? Just press this or this. Great, thank you. Sorry about mix-up of this slide because I'm using Make and this PC. But this first slide just show you we have a 9 centers, so N7 centers for the environment prediction. And environment modeling center is a place actually create all the model and go into give it to the center operation run the model and support all other centers. So we have an aviation center, we have a climate, we have a daily weather, the hydrometeorology, the daily weather, and we have a hurricane, we have a storm prediction center, and we recently joined a center called Space Weather Prediction Center, just recently. And so actually we don't have or I can say that our EMC model is actually ready for the space weather. So in order to couple with the space weather model, I use the model here. We have extend our global spatial model higher above 60 kilometers, so as higher as possible, and they maybe require 100 kilometers to 150 or something. And due to this requirement, we have to rethink of our thermodynamic variable because there's a different constituent of the gas, atmospheric gas, for the lower atmosphere and the upper atmosphere layer. And so I talk about what we actually try to accomplish. And also, we don't know how up there, what kind of coordinate we should use. So I will talk about the general coordinate and share with you the idea. And up there, the wind is so strong, it's extremely, could be 100 to 100 meters per second. So semi-Lagrangian, we cannot avoid it. So we have to use it. Usually, the reason we actually N7 didn't really implement semi-Lagrangian as same as other center because we didn't get a very good result from semi-Lagrangian. Eurolian is still very good. So, but in this case, it's better to have a semi-Lagrangian. And the last one, the zero atmosphere approximation, it may not be valid because up there is very high. If you say you have 100 kilometers or 120 kilometers, or say even 60 kilometers, your R equal to a G, G very much like 1% or 2% of the error. And that is internal wind is 1 second is 2% error, then that could be your advection could be long, totally long. So we are thinking about the deep atmosphere, of course, that require a long hydrostatic system. And so I may not have time to show you the last one, but I do my best to show you at least the first three. And of course, when we start to think about the thermodynamical, we start from the idealized case, low, and because we are consider different cases in this modeling system, and no matter what kind of cases you share the same equilibrium temperature. So but you can have a different pressure and different density. So it turns out to be turn out to be your each gas has a same shape of the total P over rho RT, and all here is we specify by the specific value of the density of the gas. So in this case, there is no such thing of virtual temperature or AMR labeled before. So we can really much general. And if we start, when we start from internal energy and with the conservation quantity, and also the CP-CV relation, you can get a thermodynamic equation like this one, the CPT. But the CP here is a function of Q, so it's in these times, it's not constant, so you cannot move out. So if you want to solve it, you have to spread the equation, the second one, by your CPQ and whatever the temperature in the Q. But that will become very tedious, so we introduce a Poconos variable called entropy, the CPT as entropy. And so the thermodynamic equation can become the low left side of the equation. And that's the very same shape as a temperature. And also they share the same characteristic of potential entropy. Because when Q equal to 0, you can just manipulate into your mass. You get d theta dt equal to 0. And in the adiabatic case, it should be potential entropy. So all this will be considered in the modeling. And after that, your temperature is not your thermodynamic variable anymore. You are using entropy, so you have to change all other place with temperature by the entropy. So the pressure gradient force is the place we change it, and the hydrostatic place we change it. Okay, and after that, the equation I think we can look at the textbook to find out how to change from Z coordinate to general coordinate. So I don't want to repeat how to derive it, but we get a general coordinate system like this. All the horizontal part is by the spectrum, so it's very high accurate, and differential equation and differential equation is very, very similar. So the discretization have become the vertical part of the entire system. And all this, how to derive it, can be getting from the paper 2011. And the concept of how to discretize the equation from the differential equation to the difference equation, we have to, as I say, we have to make sure all the nature in the differential equation should be inside the difference equation. So the conservation of angular momentum, conservation of total energy, conservation of mass, and conservation of potential entropy, and even the total integral of the mass-weighted flux advection, because advection is just advection, move something from some place. If there is no force, it's not forcing. So total integral of that should be also knowledge, so it means total equal to 0. So based on this nature of the equation, discretize equation, and first we make the vertical structure like this. We have a layer, a dot part is a model layer, and solid line the model interface. And all the variables in the layer and only pressure and vertical motion is on the label. And the first constraint is, I say, the angular momentum is to be conserved. So the mass weighted, if you put the angular momentum equation, you mass weighted, it turns out to be actually you are doing integral of pressure gradient force. And you derive an equation from top to the bottom, and this is trick. But if you discretize the first one and the last one together, you get a characteristic of this one into your difference equation. And when you derive it, it turns out to be we need a pressure at the layer, So we just give an arbitrary function for layer to label to layer, and then we can grouping all the delta p is, and after the grouping, you get each group equal to 0, and turn out to be you are getting hydrostate relation. So your angular momentum conservation tell you how to discretize your hydrostate between layer and the label hydrostate relation. Or you using this hydrostate relation discretization turn out to be you get the angular momentum conservation. The second one is the total energy conservation, and if you derive the thermodynamic equation, you get something called energy conserving term, the last one. And if you derive from kinetic energy, because the total energy is kinetic energy, the potential energy, and our thermodynamic energy. So if you keep derive the, you don't need to go into detail, but I just show you how you derive it. And you turn out to be, you also get a energy conservation in this part. So, but the sign is total. Its sign is different. So when you sum together differential equation, sum together they should be equal to 0. So that is the conserved quantity. So if we do the discretization according to the difference equation in the dynamic equation, and we use that use this discretization for the energy conversion term from dynamical part and go into use in thermodynamic equation. They were automatically total energy conserved. So that is the way. After that, we get a pressure equation. Of course, that is also called energy conserving equation. And you turn out to be, you can make the difference between there and label by just half. Very, very simple way. Next one is we discretize the continuum equation, and continuum equation very simple like this way, and this one actually try to get your pressure local change equation. And if you put that local change equation into the thermodynamic equation, you turn out to be the energy conserving part is nothing related to vertical motion. It's very interesting. Nothing. It's different form. You don't require vertical motion to get the energy conversion part. Then the last one is you do the advection total integral equal to 0. In this way, it's very simple. You just use one is already one is flux form, another one is not a flux form. You put these two together. Even though your equation of vertical advection is not flux, actually you get a flux form of conservation. And then we put the potential entropy equation, go into the thermodynamic equation to get their thermodynamic vertical advection into a different form. So after that, you get a whole bunch of discrete equation, and this equation actually difference equation and conserve all the quantity in differential equation. So you use this way, going to programming your code, you should get all the natural characteristic of differential equation. To close this system, one thing, if you realize, one thing we haven't decided is vertical motion. There's no vertical motion equation. Instead, I'll give you a more complicated one. Maybe I'll give you a simple way to describe. If you specify your model coordinate by the first top layer, so ABC for the model layer is always constant. Then if we say A and C equal to 0, then B will be something like a sigma coordinate. If you C equal to 0, if A plus B PS is very much as a sigma operation coordinate. And you C is not 0, like a sigma theta or sigma P. And to to get a vertical motion, it's very simple. You do a local change of this equation. And all the ABC is locally constant. So a partial of them is all 0. And then the main part is all the partial of the variable. And you put all the equation, related pressure equation, pressure surface equation, and thermodynamic equation, the entropy equation, and you put together and you move all the horizontal forcing to the right hand side and vertical motion to the left hand side. You get a child dynamical solve, child dynamical equation, and you solve it, you get a vertical motion. And this vertical motion satisfies whatever vertical coordinate you have. Whatever you are in sigma p or sigma theta p or whatever, they always satisfy. Okay, so I start to show you a picture instead of the equation. The top is sigma theta, and sigma theta. Okay. So the sigma theta 1, actually, you get a very pink even from a mountain from low level to the top. Okay, and the sigma p you did some slope. The sigma theta is somehow a very quasi horizontal. So in the paper, actually, I show the sigma theta result, and here I'm showing some of the case. And this is a 5-day forecast of GFS with our original sigma p, and we statistically we always has in the tropical we have a core bias in around 300 millibar, 200 millibar area. But if you apply sigma theta and the entropy equation, the core bias is gone. That means you really provide a better, because in our model we have the ozone. In the sigma p, the ozone is not very direct going to the thermodynamic equation, and this will go into thermodynamic equation. So that is the cause of the reason. And this is show you the tropical area by sigma theta is excellent. The wind error is always less, and this show you the bias also for even not the sigma theta or sigma p. The green color one means it's less value than the forecast, the G operational one. So because this is the difference between the model result and the analysis. So the right hand side is a new model. The arrow is become small, and this is showing the wind also, the wind square arrow small, and this is the temperature also, wind square arrow small, and this show you another result that come from errors of group. They want to look at whether the model mass conservation is correct. Okay, and no matter how we do, the operational one is much worse than using the model. Okay, any question for this first one? Did I? Okay. Yes. Global conservation. Okay, so that's going to the semi-Lagrangian. In fact, in our center, NCEP, we have two versions of the semi-Lagrangian code. One is to follow the ECMWF's called the Seto method. Another one is my new method called NDSL. And I will talk about my method because European Center, but you can look at, you can find the paper. We know that the reason we do semi-Lagrangian is because in the semi-Lagrangian way, there is no constraint just for the numerical stability, because we don't solve the vertical, we don't solve the direction by locally. So we just like we do Lagrangian sense, we move departure one point to another point. So there is no need to have a this constraint. But in order to have a Lagrangian direction, you have to decide the trajectory, and you have to do the interpolation between the green point and the departure and arrival green point. Okay, so that becomes a different technique there. For the traditional way, most people do is we use green point as arrival point, and we search for the upstream to see wind come from where. And after that, then we iterate to find the good solution for the departure point. And or another way, you just go ahead to say, okay, let's go forward, and we find the trajectory for the forward. And in this way, you need to iterate to find the point or end, because that is nothing, it's just arbitrary somewhere. And if you consider the conservation, then your density times your share should be equal to your departure place of the mass should be equal to arrival place of mass. That's a mass conservation. And you can see arrival point is okay, it's a regular size, but the departure point is irregular. It will require a lot of remapping to become really complicated. So I propose one method called central skin. That means the trajectory is determined by green point. Because your green point wind is already there, you don't need to iterate. So you just move from one point to another point. So departure to arrival immediately get it. So no iteration. But you need to interpret in departure and remapping from arrival point to a regular one. And this is the comparison of actually which method is good or bad. Actually is difficult to say. But for the central scheme, you don't need to do the iteration for the wind. Maybe accurate. But for the mass conservation sense, you needed to the same thing. You needed to you needed to interpolation in the share from departure to arrival, and that shape is even odd in the arrival point. So the central scheme requires some attention. So I propose even further, say we do splitting in the sense of the space and the time. So we do one direction from we do the U first, then do the V. Okay, do U first, then do V. Of course, the wind is here. Wind of UV here may not be the same as UV here. So we have a so-called splitting error. Now we can correct a little bit by doing this way and that way and adding together, or we can do this time step using UV and this time step using VU. Okay. And then we can actually get away from the bias. And this supposed a movie, but it's okay. It's supposed movie go up if something. And let's see. And this supposed goes through the pole. I can show you the final result, and this is at the North Pole. The color one is the let's see. This is 3 days later. The color one, the black one is the analytic solution, and color one is the marble result. It's actually pretty good. And this is 6 days later go to the equator, and this is 9 days later in the South Pole, and this is back. So there is still something not quite well here, but if we calculate the result, it's very similar. And that Jinli has some concern, say maybe we should try something like that. Okay, so I tried to use a very close resolution and try that, and that is the North Pole, equator, South Pole, and back. So it's not too bad. Okay, so if we look at the result of the score, the color one means is best, and I just compare with SJ's with $100. And I actually show this. But if you go to the mass conservation, you can use this diagram to illustrate it. So your wind at each point and then go to another direction, and your mass of when you are direction you move, this mass equal to this mass. So the mass sum together is always conserved. So this is conservation. So we do X direction, then do Y direction. So it's because one direction is conserved, another direction is conserved. So it's totally conserved. So it becomes very simple. But the point is, when we do the mass conservation part, then something we have to take care of it. If it's only one point, you move one point to another point, actually it's unconditional stable. But if you consider mass conservation, it becomes conditional stable. You have to make sure your share is not negative. Okay, so if this is the departure, you go to the arrival, and if your wind make your departure point become negative, you have to make an adjustment, and the solution is published with some U. And the condition is very much like the Eulerian condition. It's still wind, but it is divergent. Another thing is I have to make sure the divergent part should be conserved also. So if you are a non-divergent flow, you should not generate divergent. And in order to do that, I adapted SJ's finite balance measure. We move a point to another point, and use the arrival point wind to do the last direction. And that turned out to be not too bad. And when we tried it in the sphere, we find out in the pole area still has some problem. So looks like the clock is not moving. It's kept 23. Okay. So, change. Okay. I decided to slow down. So we find out that the polar area using the mass conservation is some problem. So we may need a higher accurate method. So if you look at the arrival and departure equation, and you start to derive from the divergent part, divergent equation, divergent part, you can turn out to get a formula for this. And the divergent part, we can use spectrum models divergent value, because that is very high accurate. Also near the pole is very, very accurate. So instead of using this way to have a mass conservation, you use this way to get a mass conservation. And turn out to be corrected. Okay, so if you started give a constant value everywhere, when you apply this mass conservation part, you get after even 100 whatever step, all the constant value is equal to 1. Okay, and you know that this is non-divergent flow, but you are doing the dimensional spreading, so it may not be your partial X may not be 0, partial B, partial Y may not be 0, even though they sum together is 0. Okay, that's the purpose. And so this just show you how good of the one is. Actually, it's not really one everywhere. It's one and one point something. That's the very high truncation. Okay. Then we implement this semi-Lagrangian into the NZGS, and when we use the dimensional splitting, then we don't need a halo, because when we can have an x direction with all x value there, so we require that for the conservation. And when we do the north-south part, we need a north-south part point. So in a sense, that the MPI decomposition should be to the transpose. For example, this is 4PE, and your north pole south pole can split into 4, and after that you transpose that into this one, so you get another 4. So you solve that x direction, and because it's a circle, so it's easy to conserve. And this you go to the north pole, south pole, north pole. So it's also a circle. So there is no halo required for solving semi-Lagrangian in this case. And how about semi-implicit? And I don't want to go into detail of complicated one, but I show you a simple equation, because all the equation has a direction, the total delivered part, the time delivered part, equal to forcing, and forcing can split into linear and nonlinear. In your nonlinear part, you can put a implicit, n plus 1, to solve together. So you have a direction, it's an arrival point, departure point, and this is the meter point. And in order to save your direction, because you have to move your value, all the value, going to the same point in order to calculate. So I also spread the mean point forcing into at the arrival point and the departure point. So I spread all the term into that side, arrival point, and this part, departure point, and put everything into x. So what I do is very easy. I just adapt x by NDSL. After the NDSL, then we can solve n plus 1 value at the arrival point. And arrival point can solve in the good point. And so I show you some result. This is T126 there, and because it's similar Lagrangian, and if we starting point of moisture are positive, then we can have a positive direction. So upper panel, the green value is negative because there's a spectrum there, so the negative value, and bottom one is no negative value. So all the previous people like it because they have to treat the negative moisture, and that's not physical. And this is another example for zonal value for T-A78 compared to operational, and you can see they are very similar after 180 focus hour. And this shows you horizontally of the wind and 1 day and the 5 days, and you can see it's really similar except the polar area. And this is the rainfall part. And so the NDSL is the similar Lagrangian implemented, and no change to the MPI because our MPI is already transposed in X and Y because of the spectrum transform. And so we don't need the actual treatment of the polar cap, and we don't treat the mountain recently. Semi-implicit, semi-Lagrangian is forcing together, and we can have a 4 and 5 times larger of the time scale. Any questions here? And okay, go into the last one. It's Riemann solver. Okay. or because too diffuse because we interpret a lot. We interpret departure point or also interpret other point. So we do X and do Y and do two times. If we do two, it's much more diffusive. So, but the result is beautiful. So it's the most because diffuse. So we need a higher and higher resolution. Next one is Raman solver. And we find out the Raman solver is one-dimensional method, and our NDSL is also very much one dimension and doing another dimension. And using the Raman solver, we change equation. So all the gravity wave or sound wave are going to a direction. So it become it's become stable, automatically stable because semi-Lagrangian is conditioned. And I will show you the zero order equation result. Okay, so this is the zero order equation on sphere. And if we make it simple using the coordinate of the line, then the equation can be make a matrix like a top. But we know that the Raman is one-dimensional, so we have to solve the major or the frontal propagation point. Instead of immediate spread, it's into lambda or phi direction. So we don't know what kind, each point we don't know what kind of the frontal propagation direction it is. So we put a arbitrary k. So it's a k lambda, like this form, and determine an arbitrary given Raman invariant dimension of the direction. So in that sense, you can put your equation into this direction and do some manipulation. You get like a one-dimensional type of equation. So on a one-dimensional type of equation, you can, because right now it's a partial k, and partial lambda and partial phi, then your equation become like the type. Then you solve a Raman characteristic by finding their eigenvalue and eigenvector. It is more complicated than put all the eigenvalue vector matrix into the solution itself in the top. The outer lab, you get to a two-dimensional again. So, but you are actually solving the one-dimensional frontal propagation. Then finally, you get a Raman characteristic equation, and D part is the Raman direction. So that is actually 0. So this is 0, and this is different direction. In this case, the propagation is perpendicular to it. Then the final is we want to how to solve that the decouple equation for this, and we find out the first condition. The first condition here is not easy to solve, but the second condition is much easier. So I use this formula, this condition to solve the total equation. So your equation becomes this, and we have a Raman invariant over the this one and this one. So if there is no forcing, it's dr1 dr1 dt equals 0. So that then your forcing part is no gravity wave in there. So in this sense, it's very stable, and you can solve it very simple. And after you get a R1, R2, R3, you can using the relation to get your H and the U. So we program this into using Howard's way, and in this run, we don't need a spectrum, and we don't need to apply the implicity, and it's only the direction part. So it's becoming very simple. So this is the color one is day 0, and the non-number black one is after 7.9 days. So the result is quite good, and this is shown in the hemisphere part side. That's easy because they are two hemisphere symmetry. And this is after 16.25 days later, compared to initial and after that. And this is 16 days, this is 25 days later. We have a little bit noise in the pole, but we later on we apply, we reduce screen, get a good solution. So come to the conclusion. We'll give 10 minutes for you to get the question. So in order to couple with the space model, we actually enhance our global model to have a enthalpy equation as a thermodynamic variable. In that sense, actually, our system can modeling different atmosphere. Even we can move to another plane. And we're using different semi-Lagrangian direction. We don't know which semi-Lagrangian we will choose so far, but even finally, no matter which one, we have to consider the general coordinate and the enthalpy equation. And we are in the stage actually to go into the deep atmosphere with ER. That's it. Thank you very much.
So Henry has left us with time for a few questions. So if anybody wants to ask.
Yes.
Regarding the semi-Lagrangian adduction, for a given delta T, how many MPI communications do you require?
MPI communication.
Yeah, parallel communications.
Sure. If you do everything together, if you do this, I just show you a layer, right? Actually, if you do, we should say like all the grid points actually communicate. But if you do two-dimensional decomposition, you are actually in the subset of, for example, K from 1 to 5 in one group is 4. And K from 6 to 10 is another 4 is another one. So they have a subgroup to the transpose. So it's not too bad. But we know this part actually is very time consuming in the sense. But if you do the older way of the halo, you have more grid point, more node, you have to increasing your memory because you have overlay, right? This one you don't. Right? This one, because memory is already there, and all the grid points are already there, except we just split into a small point.
But there's a time split. That means delta T by 2, you have to update the field, and again you have to adduct. You have two adductions of X or Y directions, right?
Yeah.
Two orthogonal directions.
Yeah, that's right. So usually we always do X, Y, Y, X. We do X, Y, and next time we do Y, X. So actually we transpose. No matter what, in the spectrum we already have X, right? Then we transpose to Y direction for this, and we do Y. X you already have it, so you immediately do X and transport to Y. Then you transport back. That's right. So one time step you need to transpose.
Okay.
Yeah.
Okay.
Oh, that's your question.
Yes.
Sorry.
Can I ask one more question?
Sure.
Follow. Oh, only one more question. I didn't quite understand why do you want to use the Rayman solver for your semi-Lagrangian model? What is the main advantage of that?
The reason for that is when we do the semi-implicity, we actually Riemann sub is maybe also the same thing. The implicit part actually you truncate the high frequency. Riemann part is you move everything gravity wave or whatever wave group by itself.
Okay.
So I think it's more accurate using.
Thank you.
I have only one clarification. Generally, we use space weather, the disturbance in the ionosphere, magnetosphere because of the solar disturbance. In what connection you are using the term space weather?
Maybe you could repeat the question for the speaker.
The question is that space weather, you are talking of meteorological weather, and we use space weather and interplanetary disturbances in the magnetosphere, ionosphere caused by the solar flare or geomagnetism. So, what is the connection? Why you are using the term space weather?
Oh, why we use this model for the space weather? That's right. Yeah. The reason is we actually extend our model very high up, and up there we do the coupling with the space model. So if there is a solar wind, whatever, they need the heating and they need the area parameterization, whatever there. So that part actually we couple. Like we couple with the ocean through the SST, right? And that is because the layer is different density, so we can using a layer to couple. But up there, they are more physical boundary. So the coupling looks like a whole bunch of space, three-dimensional. So we have to provide our wind, our whatever to the space model, and space model sometimes reflect us the heating into the solar wind, whatever. So we couple together. But in order to do that, we cannot use the density is changing a lot. So we cannot use a low atmosphere or gas used for the upper layer, right? Because that gas is totally different.
Okay, we have time for one more question. Yes. You said
different kinds of cup.
That's right. We can have a whole dimensional model right now. With whole dimensional model, because of this, we can take care of the layer at the bottom here and become one model to service for others.
okay, well, thank you, Henry. It's very interesting. Thank our speaker one more time.
Thank you.